So today we're just here at Melbourne University to present to the students about things that I wish I knew from university. We'll see some questions as well, so hopefully it's enjoyable and we all learn something. My name is Brendan, you're a structural engineer. Now let's get into it. Anyway, I'm going to be presenting on stuff that I wish I knew when I was at university. But I'll first start off a little bit about who I am. I probably didn't take what the most traditional path is, where most people think they start at a big firm and that's where they go from there. I started at a small firm. We had about 5-10 engineers, but it's really where I cut my teeth as an engineer. Working on smaller projects, I got to work on them from start to finish, which allowed me to have a more thorough understanding of engineering and get a more holistic approach. I also got to deal with clients more one-on-one and doing fee proposals and all that. It gave me quite a good rounding position when I was first starting out. And then starting at a big firm, you might be it's good, you get to work on bigger projects. It's a little bit more exciting, but you'll be focusing just on column design, just on load rundowns or slabs. You don't necessarily get that whole holistic approach until later on, because there's a lot of complexity in a big building, where a little building, someone can help guide you through the design process. And when you're looking at big and small buildings, they're really the same thing. They've got the same load paths, they've got similar complexity. So you can learn quite a lot through that repetition of doing that smaller project. After I got my foot in the door at a small company, I needed a little bit of help to get my next position at Hyder, which is now called Arcadis, which I had to use a recruiter to get in there. But after I got in the door, it was definitely a lot easier moving up the next steps. So I spent a couple of years at Hyder, and then I moved into WSP. And this is where I stayed a majority of my time beyond my first company. I actually had to relocate up to Brisbane, which was really good, and it was a really good environment. And I would also recommend saying yes to opportunities. Opportunities obviously lead you in the right path. So up there, I worked on a really big project called Queen's Wharf, which is one of the biggest projects in the Southern Hemisphere, where I got to run it from start to finish for some of the big towers, which really got me a good grounding. And this is where I moved into more of a technical side and being one of the technical leads at WSP Australia. So later on, I was definitely one of the technical heads, and I was getting flown around Australia to provide guidance as a whole nationally. Now later, I've actually moved on from WSP now to a company called Zuru. Zuru are looking to disrupt the industry through developing modular buildings. Now, when we say modular buildings, they're more than just modular buildings. You can have any size, scope of building structure, and really reducing the cost of construction to help with the housing crisis. So we're really looking to disrupt the industry and making what has not really changed in the last 20, 30 years, and make a big change and moving buildings into the manufacturing side to really reduce the cost of construction and helping guide that and hopefully disrupt the industry. There's something that will be better and bigger and have more opportunities for everyone, hopefully cheaper housing prices. Something that's a bit odd about me as well, which some of you may know or some of you may not. I actually also have a YouTube channel where I talk all about structural engineering, helping with my communication skills as well, and helping guide other people for stuff that I wish I knew, some design concepts. I try and keep it more broad and topic to keep it worldwide, global than just Australian standards. As I think, engineering is really the same, doesn't matter where you are. Physics doesn't change. But so the same concepts that you apply in Australia will apply in America, New Zealand, or even into Europe. So what is engineering really about? Well, some of the engineering, you talk about the hard skills, you're designing columns, slabs, walls, and beams. And you're also really solving problems. That's probably one of your biggest tasks. There's a lot of time the client may have a problem. They don't actually know what that problem is. So you've got to listen and understand for what their problem is. But does anyone have any idea of what our most important skill is? Anyone? You may think it's engineering or your ability to engineer, but really our most important skill is our ability to communicate. Everything that we do is a form of communication. It doesn't matter how good our engineering skills are. If we can't communicate our ideas, it's really not that useful. So our most important skills are our written communication skills. So that's like our emails, reports, site inspections, advice. And one of the biggest tips I have when we're talking about our written communication skills is understanding how we write it and who our audience are, because we want to make sure that we're targeting to the correct people. A lot of time at university, you're focusing more on that technical aspect as you're presenting something technical to someone who is also technical. But out in the industry, you've got a broad range of experiences from architects to builders that have different skill sets, that have different problems. So you want to make sure you're targeting the problems for them. So they need to understand what the issue is and how it affects them. So making sure that you're targeting it. The other one is knowing the difference between passive and active voices. A lot of the time, we as engineers, we write in a passive voice, which makes it a little bit detached and also makes it a lot longer. We want to be writing in an active voice, which means it's more engaging and short. So the shorter the better, especially when you're going into reports that someone else needs to read. They only really need to know the information. So we don't want to make it very verbose. We want to make sure that we've got either dot points to try and really consolidate it, or writing in that active voice. So understanding the difference between passive and active voices is something that's also really interesting. Something that sometimes also happens is a lot of time at university I found they recommend that you justify your text. So it looks nice and square. As engineers, we like square edges. However, when you actually look into it and how you read text, it makes it a lot harder to read. It slows you down a lot. So you always want to make sure that you're justifying to the left. The distance between all the words is the same, so it makes it a lot easier to skim read. Where if you go to the justification, it really slows people down. Now, our verbal communication skills, so it's whether we're presenting technically, like I probably am today, we're presiding in meetings, or just providing instructions on site. This is where we need to improve how we communicate to people, understanding the different ways we can communicate in the verbal sense to make sure we're interacting properly. So again, it's all about knowing your audience and targeting it to the correct person. And now, even our drawings. Now, this is probably where our key skills come in, because this is what we present to the client a lot. Our drawings are a form of communication. We need to describe to someone how they are to put the building together. So the explaining up of structural drawings, even sometimes sketches for advice that you need to provide. Even providing alternatives, also explaining concepts. And this is where you're going into, pictures really tell 1,000 words. It can take a lot of time to describe something in words, where you can draw one picture and tell a lot more from that single picture. Even in combinations of words and pictures is typically your best solution. But communication is not just about communicating. It's not just about you speaking out. It's also about listening. You need to understand what their problems are so that you can target your information to the people that you're actually looking at. So making sure that you're looking about the problems they have and saying how you can solve their problems through the problems that you have. So by knowing what their problems are and targeting your communication in that way will make it better for them to understand and take your concepts back. And if you're also solving their problems as well, it means you'll win that next job, which makes you more valuable to the company as well. So effective listening is probably one of the most important skills in communication. It's not just about you outwardly, but also listening to understanding what everyone's problems is. The other one that we do too often is focusing on around sandbox. Because when we're designing a building is not just structural engineering, it's just not mechanical, it's just not civil. It has a big, broad range of people that need to come together to have a building. So when you're looking at something, you need to understand what the other problems are and focusing stuff outside your sandbox, as you may be able to come up with a solution for their problems. Just because you know the structural engineering side, if you can also understand their problems, you may be able to make them merge to come to a better solution for the project. As you can see what their problems are, so where can they put penetrations through slabs? Where can they frame something up? You know that stuff as a structural engineer or as an engineer, where the other guys may not. But if you understand both of them, you can come up with a better solution for the project. As not just one person needs to come together. For example, we forgot the deflections on the beams. It means that we need to make the beam steeper. Well, that does affect. It has knock-on effects. You have bigger facades, you have bigger complexities on the design, increasing costs of the buildings. But you may be able to frame it up a different way, adding in additional columns. There's definitely a number of ways that we can potentially solve it. And going through those solutions with the client or the architect will also help it. Stormwater drainage, they need penetrations through your slab. You need to make sure the drainage is going through there. So knowing where's the best locations for it, you won't always get it in that best location, but knowing what the implications are of not putting it in that solution, so knowing how it's framed up. Or even increase building occupancy. So what would that do? That would mean that you potentially need bigger plant areas, so you've got bigger loads on certain plant floors. So just knowing how that actually gets through there and the knock-on effects of different aspects to your design. And learning, probably one of the biggest ones that might be drilled into you, it doesn't really stop at university. You've only really started your path at university. So when you're at university, you want to try and increase your verbal skills. And it's all about trying, reviewing, and repeating. Everyone's going to make some sort of mistakes at some point. You want to make sure you're learning from them, and you don't really learn by not trying. So it's putting in that effort, understanding what you're doing, and actually learning from those issues. So when I'm at university, because it's not stopping there, there's a lot of stuff to still learn and knowing a lot of differences. But what should we focus on at university? I really think understanding mechanics of engineering, how things go together, depending on what you're doing, is like, I'll bring an example of structural stresses, is knowing how stresses flow through structures. What is the interaction between loads, shear forces, bending moment diagrams, and even deflection? As this will allow you to understand structures more thoroughly and how forces flow through structures. This gives you a better understanding of how things actually work. This is what university is really good at. It's teaching you how materials behave. Codes always change and things adapt. But if you have a thorough understanding of mechanics, it doesn't really matter because engineering is the same. You'll come to the same conclusion. Also, it gives you a better understanding of why the codes are focusing on different aspects. So at university, you should be really getting those mechanics of engineering down to understand the things. Another one that happens quite often is the fact that when you're starting to learn, you can get to quite a peak of confidence thinking that you know a lot of information. This is commonly called the Dunning-Kruger effect, where you think you know a lot, but there's still a lot to learn. This is very true in engineering. Especially when you come out, you'll find there's a lot of learning to get to that next step. Sometimes it can take a lot of effort to go over that hump. But if you do then realize that you don't know as much as you do, that's a good thing because you're having self-awareness of what you need to learn. So it means that you've got to be constantly learning and pushing your boundaries and questioning what you know as well. Because sometimes just because you think you know it doesn't mean it's the correct thing. It doesn't hurt to actually be questioning what you know, making sure you're testing your knowledge and constantly improving. And this is where it becomes really hard because good design is hard to learn. It's something that can't be taught and it takes time to learn and you need people to be able to help guide you towards it because there's a lot into design, not just designing the structural stresses, but how things actually go together. And most of the time it's keeping it simple and you don't know what you don't know. As we were saying with the Dunning-Kruger effect, it's a lot hard to know something that you don't know. So the good design, it just comes to getting your hands dirty, learning from other people, taking those opportunities that you see that you can have through internships and other areas and learning from them and getting your hands dirty and doing a lot of the numbers. Unfortunately, when you're first starting out, it's quite hard as you need to get your hands dirty and do a lot of boring tasks a lot of time to get an understanding. It might be hard to go, I want to get into the more complex stuff. I want to start doing stability design. I want to get away from just columns or slabs. But there's still a lot you can learn through how structures behave just by doing those simple tasks and getting that repetition in, because then eventually there'll be an aha moment and you'll understand how things are actually coming together and how things are actually performing in reality. The other big one is knowing the difference between analysis and design. A lot of the time at university, you're being taught analysis. You're looking at how the stresses are, how much the bending moment capacity of a beam is, where the loads are going. However, design is about bringing that all together. So what is the site constraints? How can I put something together? How are they actually going to build it on site? So there's knowing a difference between what you're actually learning and how you actually design something. So it's good to understand what the differences are. And I'll bring you some examples of where sometimes you have to look at things in a different way. And this is knowing the details. There's actually a collapse, the high walkway collapse, which you may or may not know about. It was a tragic failure of a walkway where it killed over 100 people. And it was some of the littlest details that actually matter that caused this failure. So if you look at the original design, it was quite simple. You had a bolted walkway that was bolted between two areas. You had the bolt between it, and so the load was just going through and it was carried by the bottom section. So the whole tension capacity was occurring in that rod. However, during construction, they were realizing this was going to be a bit hard to build, so they made a simple change. What was that change? They moved the connection off from each other. So there was one was bolted at the top and then they have another rod coming down offset. Probably the easiest way you can think about this is if you've got a climber climbing up a hill, he's climbing up, you've got the rope going between the two people, the rope takes all the pressure. But now if you were to untie that rope and tie it to the climber above, he would have to hold both his weight and the weight above it. So what that did, it doubled the capacity of the top connection, because not only does it need to support itself, it also needs to support the weight of the structure underneath it. So how this actually happened was there was a design change. There was no follow-up, and the steel manufacturer had actually changed during the process. And during that change of process, they didn't actually realize that there was actually a change to the design that was never actually designed and approved. And so they were never actually checked. It was never actually signed off with. Now, was it anyone's fault? Who knows? It was just a bit hard between changing people. But the proper design change and registers weren't followed. And some of the little details weren't there. It was actually even described during the construction, they found this thing was actually not too great. They were actually seeing some problems with it. However, no one said anything. And probably the scariest thing is, even if it was designed properly, it was still 60% under capacity. So the original connection didn't even work as is. So there was a problem with the design change that actually caused an issue to the structure. So what can seemingly be a small detail, the whole beams and structures work, can cause a major tragic event to occur. So that was some of the stuff we were saying, say something. There were significant defects observed during site by the building surveyor and other people cladding it up. They didn't really do anything, and they cladded the position up so you can no longer see the defect. So when you're on site, it's not just about looking at what you're looking at, but looking around to see if you can see anything else beyond your scope. If you see something, you obviously should speak up. There may not be something wrong, but it doesn't hurt to actually say something. Look, this doesn't look great. It's all our responsibility to make sure the building is going together effectively and talking to people about stuff we observe on site and not just focusing on what we need to look at. So if we're looking at stuff over here, we may see something over the other side of the site and looking at that and bringing it up if we think it's not right. So Jack Gillen presented many times on this, and his purpose was to actually make people realise the responsibility that we have as engineers. You know, we want to make sure the building is safe. We can affect quite a lot of people. So actually give people, scare the living daylights out of people to make sure that they understand the responsibilities that we have as engineers and how we can affect many lives. And because being an engineer is really important. And it's the one thing that you should always do is always do the numbers, not just assume it's okay, not just using those typical details, assuming they're correct, but going back and checking for them, making sure they are acting as you think. You know, we're busy at times, but it's always good to go back and check those little details and make sure they're performing as we expect. And something that I would actually recommend that a lot of people sign up to is an organisation called CROSS. So what CROSS does, it allows you to anonymously report events that you see on site. And what they do is they do a monthly newsletter around about the stuff that they've seen and things that we can follow up on. Something that we can do better as engineers is actually talking about some of the failures that we see and learning from them. We don't ever want them to happen, but we should make sure they never occur again. And CROSS is trying to look to address that by doing anonymously reporting so we can learn from other things that people have seen on site. They might be a failure, but even a near miss is something that we want to make sure we avoid in the future. So I'd recommend there's different organisations around the world for CROSS, and there's signing up to a couple of them and learning from their newsletters, as you can see some stuff that you can try and avoid in your design. Another thing that as engineers, especially as professional engineers, that we can be affected on is from priming. Now, this is something that was actually tested even through something really simple. And this is known as the Florida effect, where language can affect the way we behave. When we hear the words bold, grey, wrinkled, and forgetful, what does that make you think of? Well, it makes you think of being old, obviously. And what they did is how they primed someone. They had people in one room and they make them move to the other room across the area. So what did this do? Well, the people that were primed with these elderly words walk slower from that one room to the next room. So the test wasn't actually in the room that they were getting taught about or the next room. It was the ability from them to walk from one distance to the other. So just by being primed with these words, on average, they walked slower. So this can actually affect the way you design things. That's a really good example of this where design expertise comes into place. Now, this is from the Citicorp building in New York, where they potentially had a near miss. It didn't actually fail, but it was pretty close to. And it was expertise bias that actually caused this event to occur. And this was designed by a world-renowned team and one of the most prominent engineers in the high-rise buildings at the time called William Miller. No one would question about his expertise in high-rise buildings. However, this is what led him down the long track to actually miss something that was really obvious. You see, the site had a really unique feature at one of the bottom corners. It had the St. Peter's Church. That needed to be around the bottom corner. And as part of the site, they needed to make sure they didn't destroy it. So they needed to design a solution that would come up with avoiding that location. So it means one of the corners of the buildings can't go down as they need to frame it out. So this is where the real problem lies, was from this framing. And we can see this in this picture from the bottom. So you can see the church down on the left here. So you can see we've got this unique feature of this central column. Was a solution that they came up with to solve this problem, which was quite innovative at the time to come up with it and solve what is a complex solution actually work. They came up with this solution where they've got this frame on the outside of the building that drags all the load back to that central column, making sure it flows down the building and solving that huge cantilever for the structure, as each floor was cantilevering down effectively to get to that load. Now, that solved the gravity problem. However, buildings can rock backwards and forwards from wind, and how they behave is quite dynamic, especially when we see structures, they can move all around. When you've got the wind going one direction, you're okay. When you rotate it, you might be able to see the problem here. The columns have actually moved closer to each other. So it means that crosswind response becomes a lot worse. You don't have that big cantilever. So typically on a typical building, you've got the primary columns on the outer edge. So by having this, it's really strong in a crosswind response as you still have a really big lever arm. So if we look at that and we assume that that is a one characteristics, right? So that's a big one. So that's how much load you can resist. However, when you rotate it, crosswind response, it gets better. But then when we pull the columns in central, we're now 60%. So that load has increased. As your lever arm has reduced a lot, your load has significantly increased on these columns. So this is what the real design error was in this design. It was overlooked by the design team. This building was actually built. It wasn't until much later that it was actually notified. It was actually found by a graduate engineering student called Diane Hartley. She was obviously given the project as part of her design to see how it was coming together. And she was doing the numbers and couldn't actually get it to work. So she reached out to William Miller and went, I don't understand. Obviously, I've done something wrong. Being a graduate engineer, you're thinking they're obviously a world-renowned engineering team. They've done it right. So this is where Lemessurier, knowing that something was wrong, he actually stepped up. And this is really where the ethics of engineering comes in. Seeing something, say something, and taking actions, especially if something's wrong. So despite his reputation loss, despite what it would cost him, he stepped up and actually took actions to fix the problem. He worked in, day out to make sure it was organised and fixed. They even put in warnings around the site because when they did the numbers, if they had a really big event, this building could have fallen down and collapsed. So what they needed to do was strengthen the outer structure to make it work and support those details all the way down to the bottom. So despite him doing something wrong, yes, they missed something. It's really critical. Everyone makes mistakes, but he also then took the time to fix that problem, despite what that would affect him or how that would affect him in the future. So how can we avoid this? It's always about challenging our assumptions, taking more of probably a scientific approach. There's always assuming that you're wrong and trying to disprove what you know instead of proving what you know. A lot of times engineers, we take it from one aspect of trying to prove something instead of trying to disprove it. And then always asking questions. It doesn't matter where you are, if you're at the start of your career or the end of your career, always asking those questions. You know, the only question you don't ask is the dumb question. It doesn't hurt. You could either be right or wrong, right? If you're wrong, you learn something. It's a win-win situation. If you're right, you may have picked up on something. So either way, you've actually learned something or actually found something that needs to be addressed. So something that we should always be doing is asking those questions and making sure that we've addressed everything with the design. These are just some other tips that I also have is a lot of time with engineering, tasks can be quite overwhelming, especially if you're designing a whole building. So how can we do with that? We create lists. We break it down to simple forms. If we break it down for those simple forms, it becomes a lot easier. So doing from task 1 to task 2 to task 3. And you'll find that you'll get it done much easier. So you want to be breaking down those complex solutions, creating a list and using those lists in future designs as well. Writing down summaries at the start of your complex computation packs as well. If you write a design summary, see someone else needs to pick up your computation. So you need some sort of guidance at the start about how you've approached the design, some of the loads that you've approached and how you've actually gone through the design. It's not just doing the computations, but also having like an executive summary about the different approaches that you've taken to your design. And also with your designs, you don't want to overcomplicate them most of the time. The simplest solution is often the best. And as I was saying before, something we always need to be learning is constantly asking questions. Now, when you're asking those questions, it's not just looking for someone to have a solution. At least have a go. Have an assumption of what you think it is. Doing some numbers and saying, this is how I think it's going to be framed up, and approaching it in that way. Even if you're wrong, it doesn't matter. You've had a go and you'll learn from it. Where if you're just looking for someone's solutions, they keep giving you that, you'll never learn. You all constantly have to go back to them for that solution. Where over time, if you're constantly trying to get to the right answer, you'll find that you'll be more right than often than not over time. You'll improve much quicker. So it's a win-win, really. It doesn't really matter how you approach it. It's not about being right or wrong when you're asking those questions, but at least coming up with a solution about how you can address it. Another thing that people often forget is the fact that we're actually the pilots of our own career. It's not up to your manager to actually guide you about where you want to go. They can help you with where you want to go. They don't really keep track. They're doing their own things about the stuff that you've worked on and the stuff that you haven't worked on. So you want to make sure that you're keeping track what type of projects you've worked on, what type of project you want to work on, what do you enjoy. So it's about focusing your career in the right path, about where you want to be going. So it's about being that project. And I'll not shy away from doing those smaller projects. As I was saying, is you learn a lot from those small projects. You get to learn them from start to finish, and they just scale up to those bigger projects. I learned quite a lot from working at a small engineering firm, working on small houses that were really complex, but I actually applied them to the bigger buildings. It makes my designs approach a lot easier. And something you should always be doing is also trying to seek out people that are better than you. If you're the smartest person in the room, you're in trouble. You want to make sure that you're the dumbest person in the room because that's where you can learn and grow. So we'll have a question time now. If anyone's got any questions or anything.
I'm just curious, like how much time do you spend on your YouTube channel per week? How often do you?
Probably 8 hours, 10 hours or more. But I'm trying to post once a week. At the moment, it's about 3 times a month. But I've got about 100 videos up there at the moment. Definitely my older videos are a lot worse. You'll see them. The YouTube's also helped me with my communication skills a lot and help represent because you can see how people interact and even listening and recording to myself and going, oh my God, did I really just say that? Mince my words together and go, oh my God, that's terrible. So something, even if you're not going to do a YouTube channel, it's obviously worth recording yourself and seeing how you present because it gives you better feedback. Sometimes it's really hard to listen to. Eventually you get over it, but it definitely does help. What, some time management? Yeah, so time management is a very hard one because when you're looking at what you need to do, you need to prioritize things. A lot of times, especially as a graduate, you'll be push-pulled everywhere. You'll have different people telling you to do this, different people telling you to do that. To some extent, you need to prioritize yourself, but if you get too busy, you really need to speak out and go ask your manager going, what is really more important? I can't do all this task. You know, I can only do this and that. And sometimes it's even segregating our time. I remember when I was getting at the peak at WSP, I was getting over 100 emails a day. Now, if I took time to actually read them, it wouldn't work. So it's also trying to segment out different times and blocking out times to actually do the design task because you don't want to get interrupted. Every time you get interrupted, it takes you to do it a lot slower. So it's about, you don't need to respond to that email straight away. You don't necessarily need to answer the call. If you're actually in a meeting or something, you wouldn't answer that meeting. So if you need to get something designed, you can actually call someone back if you need to. So it's also about understanding what the most critical tasks are and then even talking to your manager or the client, going, we can't do all of this, we only do one or the other, and working out what to focus on properly. But time management, like sometimes what we do also relies on someone else. So sometimes we may need to prioritize a task that doesn't need to be done right now, as we need someone else to help with it. So we may need to do that one first, so we can hand it off to someone so they have work to do as well.
So how did you end up with building structures?
Building structure?
Yeah, because as a civil engineer, you can do a lot of things, and as a structural engineer, you can do infrastructures.
Yes.
So just wanted to know, how did you end up with
Something that I was also probably a little bit enjoyed about, something that I was interested in as well, and probably even just a little bit of circumstances as well. I knew someone at the small company where I started, which is really where I started my teeth as a building engineer. But also it was probably more, I find buildings to be more challenging, more complex. Infrastructure can be quite repetitious. You're just designing one thing and trying to repeat it 100. Where buildings can have quite complexities in them, so it's a bit more exciting. You need to push the boundaries a little bit more, understanding how structures actually behave. So I really found that buildings can be quite hard. You don't necessarily get paid as much as what you would in infrastructure as well. That's probably the other one. But it's more complex. So it depends on what you want to do. I found it a bit more enjoyable than some of the infrastructure projects I've been in. It's just heavy designs and you just design it quickly and you're repetitious. So there's not much complexity in that design. Where building, especially in small residential, you're pushed to both get the complex designs, make something look good, but also do it at a cheap cost. Actually, I really enjoyed my choice of choosing buildings over infrastructure, but you can do both. So later on, I was doing both infrastructure and buildings in different projects. As moving forward, we probably need to be a bit more diverse in our things because in the next couple of years, I think we need to probably focus on infrastructure. We need to focus on defence, hospitals, universities. The residential structure may slow down a little bit with pricing, with interest rates going up, things are slowing down. You can see builders are going bankrupt at the moment. So for the short term, even if you can just get that infrastructure experience, it doesn't hurt, it helps. So it just depends on what experience you can get, as it ends up leading back to engineering at the end. So.
Did you always knew you were going to want to be a structural engineer as you were studying at uni?
It was probably even before. It was maybe not structural engineering, but engineering. My grandpa was one of the lead engineers at SEC, which helped build the power plants out in Loy Yang in Victoria. So he was actually really an old school engineer. I was growing up with him about the maths and science and stuff. Probably the one thing I always enjoyed was I wasn't great at English. I wasn't great at the verbal communication skills as well, but I was really good at physics and building stuff and solving those problems and maths. And that's probably what drew me towards engineering more so. And then I just sort of fell into civil and structural engineering is where I saw it. How did it apply? So you say university, probably what I know now compared to what I knew at university, I probably only use about 1% of what I know at university. So university is really there to get you understanding of structural mechanics, right? About how things actually behave. You actually learn a lot when you go into the workforce. Fortunately, when I was going through, I knew some people, so I started working in second year, pretty much full time. So I had quite a lot of engineering experience even at the time I got out at fourth year. So it was quite a lot of learning going through that. But the stuff I learned at university was, most of the time I don't use the stuff later on. It's good for understanding structural mechanics. The stuff I really use a lot is like the WL squared on 8. Those type of stuff that you learned in first year or second year is the stuff that I use more often than not. But the one thing that I would recommend, especially moving forward in engineering, if you want to try and progress your career, especially that transition, is doing some of those numbers, but also learning a programming language. More and more, we're going to be programmers as engineers as well. We're going to be applying it to software to increase our design process. But yeah, the step between university is quite different. It's a different approach. You've got different targets and how you approach things. Sometimes, like when I was working, lecturers say you'd always do it this way. I've been working for 2 years at this point. I know that we never did it that way. So I know that's, sometimes depending on the lecturers you have, some of them may have had background experiences in the consultancy, so they'll know where it is. But some of them have just been in the academic space and don't necessarily know. Yes, technically, probably to the letter of law, you may need to do that. But sometimes from doing that design a lot, that you'll never have that type of failure or that type of event. So you don't need to check it. The stresses are really low. So there's a big difference between that. And probably the biggest one is just understanding how you put drawings together. I don't know if they're teaching you at Melbourne. I know they didn't teach me when I was at Monash. But how drawings go together, that's probably the biggest one, is putting drawings together is what you'll do most of the time, especially when you're starting out. So that's what actually goes to the builder a lot of the time. So having understanding of how drawings are put together and the details that come into that is really important. That's probably the biggest one that I wasn't actually taught at university at all. But if you can get that experience or focus on that type of stuff, that's really helpful as well.
All right, I think we have to wrap it up.
Yeah.
We're going to have barbecue now. And if you have more questions for Brendan.
I'll still be there.
Yeah, thanks for Brendan. Yeah, thanks, Brendan.